Hi, today I will be talking about competition where either species could win. So this is interspecific competition, and we're looking at competition between two species, and we can do that by looking at the Lotka-Volterra equations and model. And so what we have are two equations right here. The first equation is for species number one, and the second is for species number two. And you can see that with the subscripts. So the subscript numbers indicate which species. That's how we can tell them apart. And the first section of this equation has the dn1 over dt, and this is the change in population over change in time, n being population and t being time. And then that is equal to basically what I see it is in three parts. So we have Rn, and that is the intrinsic rate of increase. And then after that, we have this section right here, and these are your resource limitations. And K is your carrying capacity, so you'll be looking at what your carrying capacity is minus limitations from resources and interspecific competition. And then the last part is competition from the other species, and this shows the effects of species 2 onto species 1, and that can be indicated by alpha 1, 2, and then n2. So n2 would be the population of species 2, and then with alpha, the subscripts, I imagine a little arrow going from 2 over to 1. So little arrow, and this would be the effects of species 2 onto species 1. And this could be interference like diseases, or maybe physical or chemical interference, or it could be shared resources. And so that section just shows you where species 2 affects species 1. And essentially the same thing for the second equation, except for it's flipped. So we have everything for species number 2. And then the second part where it differs a little bit is we have alpha 2, 1, and 1. So we have species number 1, and then alpha 2, 1, again with the arrows, it's the effects of species 1 on species number 2. The textbook uses a beta for this, and so we'll see that in the upcoming graphs. So starting with the first graph, we can see where both species 1 and 2 are represented, and so species 2 is shown in orange, and species 1 is shown in green. And now they have these lines, and those are called isoclines, and that is where the net population growth rate is 0. So that dn2 over dt is 0, or dn1 over dt is also 0. So basically the population does not change there. And what those do is those cross, and that would cross an unstable equilibrium point, and it creates 4 sections. And at the carrying capacities for each one, we see the stable equilibrium points. So for species number 1, the stable equilibrium point will be at its carrying capacity, and there is when species number 2 is 0. So we can see that species 2 is indicated by the y-axis and species 1 on the x-axis. And then similar goes for species number 2, where its carrying capacity is at stable equilibrium point, and that is where species number 1 is also at 0. So in these 4 sections, it really does matter where your starting point is. So this is the only outcome of the Lotka-Volterra equations where you begin matters and how you end. In this, either species could win, but it will result in an extinction. So if species number 1 reaches carrying capacity and its equilibrium point, then species number 2 will be extinct. And it really depends on the conditions and who has the initial advantage. So where do you start at the beginning, and whichever one has a better start, that one is the one that is most likely to succeed. So a greater look at this, we want to define the zero growth isocline when we do this. So we have the isoclines in orange and in green, and then we're trying to really see where things are going to go. So you can kind of follow the arrows, and that indicates what direction you're going into. So in the upper, if we start in the upper right, so if we start over here, both populations are going into decline because we're going to need to move in this direction because there's nothing in here and we're outside of that color in space. And then if we start over here, both populations are going to increase. So we're going to go that way, we're going to go towards the right, and we're going to go up. So both are going to increase. But if we're in the lower right, so where it's only shaded in green, that is where it kind of changes a little bit and they're going to be different. So we're going to see an increase in species 1 but a decrease in species 2. And if we also go to the kitty corner, we'll see an increase in species 2 but a decrease in species 1. And let's kind of go into some examples, and we're going to look at 2 different species, and we're going to look at the different starting points as indicated from this graph that is found in our textbook, and we'll also talk about why E is unstable. So we'll go through each of the letters. If we start here in species A, point A, both are going to increase, so we have arrows increasing not only for species 2 and species 3 because we are underneath the isoclines for both, so we haven't hit the isoclines yet. We have not reached that, so we are going to stay right here. And then for species B, we are outside of the isoclines, so there's this big open space, and both populations for 1 and 2 are going to decrease because we are not underneath those isoclines. For species C, you'll see that the population for species 1 is increasing, as indicated by this green arrow, and species 2 is going to decrease. D will have an increase in species 2 and a decrease in species 1, and so when we look at things and they depend on the starting point, if we were to start at point C, species 1 is going to have an advantage. Species 1 is better off. We are underneath the isocline for species number 1, and so they are the ones that are going to win in the end, and they have a better chance of surviving, and they have the initial advantage. If we start at point D, the same goes for species number 2. So we are outside of the isocline for species number 1, and that population is going to decrease while the population for species number 2 is going to increase. Now we have the unstable equilibrium point, point E. Now E is unstable, and this is a place where any random change that could move off from the point results in different situation. So anything like a large population of immigrant species, or from species 1 or from species 2, would disrupt that, or a natural disaster or a big storm. Anything that could alter the populations or the environment at all will really just remove us from point E. So we could easily be put at point C or point D, and that is why that is unstable, and all arrows will be pointing towards the carrying capacities where it results in the extinction of one species. And that wraps up what I have. Thank you so much, and I have reference. I used graphics and content from page 265 from the textbook, so if you are unsure on anything or want to read that over, it is page 265, and thank you so much.